Thanks for having me. And so, yeah, what I'm going to do is coming at this more as someone from the MRI community. What I'm going to do is really try to give a perspective of where open data sharing and open science has taken the imaging community and the opportunities that the open science movement has really provided to advance the science in the imaging community. And then, which I think also is a model for other communities, including the EEG community. And then show a bit of where I see the opportunities coming with, as Tara had mentioned, the Healthy Brain Network and those data sets which are openly shared. So just first to start off, I'll say no financial disclosures. Okay, so as opposed to a bit over a decade ago, now at this point, publicly available MRI-based neuroimaging data is abound. If one looks, this here, first for starters, is the International Neuroimaging Data Sharing Initiative, or INDI, and the varying initiatives we've had over the year, the 1,000 Functional Connectomes Project, ADHD 200, the Autism Brain Imaging Data Exchange, Consortium for Reliability and Reproducibility, or the Primate Data Exchange, or PrimeDE. These are all open data sharing initiatives, heavily focused on resting state fMRI, and of course associated morphometry, and then to a lesser degree there is the fusion, connectivity, some other modalities. But these initiatives alone have made available about 20,000 data sets. And then comes the larger community that's emerged over the last decade as well, where you can see there's just a range of different initiatives, from large-scale data generating initiatives such as the ABCD study and Human Connectome Project and the UK Biobank, to other open sharing platforms like Open Neuro. There is also Enigma. There's a range of different models for open sharing that have emerged. So now all of a sudden we're talking about tens of thousands, or as recently highlighted by one paper that pulled together a full range of MRI data, over 100,000. I believe they hit about 120,000 structural MRIs. So data is available. And as you can see, there's a range of different topics built into the openly shared data. So then really the question starts to become, for any community, as you openly share the data and push the sharing agenda and open science agenda forward, what to do? Essentially, so now what? It's really the question. What are the opportunities, really, is I'm going to step into? So the first opportunity, which is what we had tried to point the community towards with the initial 1,000 Functional Connectomes Project release, and also with efforts like the Autism Brain Imaging Data Exchange, or ABIDE, is there's the opportunity to increase the scale of science. So in each of these instances, people over a decade ago, researchers were dealing with 10, 20, 30 data sets, samples per group. All of a sudden, once you have the 1,000 Functional Connectomes Project, if you wanted 20, 30, if you had 20, 30 subjects worth of data, suddenly now you have access over to 1,000 subjects worth of data. With Autism Brain Imaging Data Exchange, suddenly you had access to over 1,100 data sets with autism. Suddenly now the scale of science changes as far as the range of inquiry one can make when you have these openly available data sets, which, to be clear, these data sets were created by looking across the globe at previously existing data sets, I should say, not open, previously existing, and basically coordinating, forming consortiums to sit there and say, hey, what if we all just pulled our data together, organized it uniformly, and we openly shared it? And that's really been the story of INDI, whether it be these data sets or things more focused like CORE, which is really focused on test-retest reliability, or PrimeDE, which focused on non-human primate imaging. In each one of these instances, it's let's take existing data sets, independently collected, pull them together, curate them, organize them, openly share them. Beyond changing the scale of questions, what one could do is, here's a paper that came with the ADHD 200, led by Damien Fair for the manuscript, where what we did is we basically asked the classic question: can we differentiate ADHD in attentive presentation versus combined presentation? That's something that was not traditionally easy to do in ADHD samples, because typically you didn't have enough of either presentation in order to be able to analyze them individually or contrast them to one another. Instead, what you typically did was just pulled across the two different presentations, which are actually markedly different, and hope for the best. But here the point was, with larger scale data sets, you can start to go looking at subgroupings or subtypes like this. And then these fine groupings, what one could do is really now start going into the area of neurosubtyping. So basically this whole vision of using data to basically cut across diagnostic boundaries or even go into heterogeneous disorder spectrums like the autism spectrum and go and look for biologically homogeneous subtypes. And one of the papers to emerging autism community was this one here by Suk-Jun Hong, where the idea here was to basically go and subtype individuals with autism based upon structural imaging, identify in this case, 3 homogeneous subgroupings. And actually, basically, the advance here was that once you actually had these homogeneous subgroupings, you were better able to appreciate brain behavior relationships. This, again, just examples of what happens when we start pooling data together and sharing it. Yeah, and of course, in all of this, what one could really take on is the issue of reproducibility, which when I looked at this paper years ago, the good thing was neuroscience was in table 2, not table 1. I mean, that was, I guess, would make someone feel a little better. But out of all seriousness, neuroscience, low statistical power, small sample size cited as key challenges. Here's an example of using the ADC 200, going back to Damian Fair's paper. Here, when an effect was observed in one site or across the whole sample, one could go into the individual sites and say, how consistent is it? So here's a developmental effect that was repeated across a number of independent sites. Again, now increasing the credibility of findings. And of course, the Enigma Consortium does a great job of basically doing mega-analysis style studies where, again, they're able to look across sites and look for consistent effects and show how consistent is any effect across sites. This is what happens when you have large collaborative initiatives and open sharing of data. Here's a paper that also came out recently from Adriana DiMartino based on the Autism Brain Imaging Data Exchange, where she took on the challenge of, well, how replicable are findings from ABIDE in 2 other samples. In this case, she used GENDAR and EU AIMS, showing that some key findings replicated in 2 samples, 1 and 3, and then a lot of them didn't replicate beyond a single sample. And then the question becomes why? Why is it that some findings replicate and some don't? And a lot of that starts making one start thinking about the sample composition, differences in the characteristics of participants, as well as also just fundamental questions about the imaging platforms used and what some of those differences might be. And of course, when you're sharing, you can start seeing things that people might not always want to look at. So for example, in the structural imaging community, there's a growing focus on to what degree is it that developmental findings might be related to head motion. And with large-scale data sets, accompanying resting state fMRI, people could come up with different trait characteristics of head motion and start asking questions about how do we, separate out artifact from valid findings, and taking on those challenges. Which these kinds of questions could be at first scary for folks because it feels like, oh, we're going to overturn all prior findings, and that rarely happens. What typically happens is one finds out that there's signal and there's artifact, and we can separate the 2 when we actually pay attention to it. And we can also learn what the limitations of prior findings are and how to move forward. Another range of opportunities emerges for optimizing processing pipelines. Just as an example, with functional connectivity, one could sit there and do, this is work by Joshua Vogelstein colleagues, led by Eric Bridgford, where they sat there and took core, test-retest reliability data set. And using CPAC, a data analysis pipeline we created that allows you to really create a plurality of pipelines, they systematically varying parameters across hundreds of pipelines. And what they wound up doing is asking which ones were most optimal from a test-retest reliability perspective. There's also opportunities like what Gael Varacqua and his colleagues have carried out, where really optimizing step-by-step in connectivity, matrix generation. In this case now, instead of reliability, they use predictive validity. And they did it in a number of different openly shared data sets in order to be able to figure out how generalizable are their findings, which is a key thing. If you only look at your data, you don't know if what you have generalizes. They also took on challenges like how to optimize your pre-processing pipelines so you could predict a site that was not previously, that was not included in the training data set. And, it took on that range of optimizations, which is a unique challenge to go after. And one other thing is, if one looks at in the fMRI literature, there's a growing range of test-retest reliability papers really helping us to rethink about how much data are we collecting, what's the most optimal data. And the thing is, almost all these papers are using openly shared data. So what happens there is now we could try to replicate each other's findings, we could extend it, and we could really ask the question of how do we improve the quality of openly shared data and data more broadly as far as our analyses go. One last thing is, if one's not convinced about the impact of shared brain imaging data on the community, I'd point you to this paper that we did a few years back in Nature Communications, which basically showed as a result of data sharing initiatives, you actually have a much broader audience. So it's not just increasing the scale of the samples that are used by those who already do this area of research, but you wind up adding in a much broader community. And when one looked in this paper, when we calculated out, and this is back in 2017, when we calculated out what would it have cost, about 1,000 papers have been published with data from INDI, or basically that subset of data sharing initiatives that I mentioned that we spearheaded. Well, just to regenerate those papers, the 1,000 papers that were used, that used data from INDI, this is independent investigators, not the people who generated data, it would have cost $1 billion to create the data needed to carry out all those studies. And instead, because of the open sharing of data, it's literally just a matter of downloading and going. So what I'm going to do for this final part is talk about, part of open sharing really is one of the things that one can do is help drive an agenda. So I come from child and adolescent psychiatry. That's where I'm a combination of cognitive neuroscientist as well as child and adolescent psychiatrist. And so when we make openly shared data focused on child and adolescent psychiatry, what we do is we invite other people to join in the analyses. What we created at the Child Mind Institute is something called the Healthy Brain Network. And this is an openly shared data set that we've been creating since about 2015, targeting an end goal of 10,000, which admittedly COVID has definitely brought some disruption to in the last year and a half. But built into this data set, what we did is we thought through a number of design things that we were after. One is transdiagnostic research. Second is to have a data set that's rich in characterizations, not just resting state fMRI and morphometry and so forth, which are areas closest probably my own analytic interests, but actually a much broader range of modalities, including EEG, actigraphy, eye tracking, most recently ecologic momentary assessments, there's voice samples and so forth. And so what happens is by having this multimodal characterizations, A, we create opportunity to create links between the different modalities, and B, even beyond brain, even if you're someone who cares about just the imaging, there's another side of the equation. You're trying to also relate your imaging data to characterizations of behavior. And in order to do that, you want to keep improving beyond just what traditional questionnaires get for us or cognitive paradigms, many of which have not been really found to be particularly reliable. So the Healthy Brain Network pulls a range of design principles together and characterizations and modalities and creates it and gets it all in a sample that even called Healthy Brain Network. It's actually about 90% kids with one or more mental health or learning disorders. And as I mentioned, there was an EEG protocol heavily developed by Simon Kelly and Lucas Parra. Simon Kelly being the one who helped us think through a number of task paradigms like visual spatial sequence learning, decision-making, processing speed paradigms, and then naturalistic viewing with Lucas Parra, which here gives an example of the multiple little movie clips that are included in this protocol. And the naturalistic viewing creates a unique opportunity to sit there and have a probe that, if you think about MRI and EEG, even though we're not getting it simultaneously, what we did is we inserted the present. It's a short clip that occurs both in the imaging and in the EEG, non-simultaneous, but because there's a common signal in the two, one could try to go between the modalities and ask questions about inter-subject correlation between what's seen in the scanner and what's seen in the EEG, as well as just the broad range of questions one gets if you only focus on EEG about inter-subject correlation, which here is a paper from Lucas Parra and colleagues that we had done some years ago, which really shows the value of the broad range of naturalistic viewing clips in there, some being less engaging and some being more engaging, some being more in flashing video screen or an algebra lesson, as opposed to a Hollywood trailer. And what one sees is interceptor correlation goes up with level of engagement. We were able to detect age and sex effects. This data is all openly available and all, as I said, present in a sample that's heavily characterized with respect to psychiatric phenotyping, also learning evaluations, a broad range of phenotyping. And, you know, in the end vision, this is work by Gael Varroquois, which I thought really is just a wonderful visual, which why would you create something like the Healthy Brain Network? In the one hand, it's, you know, any given modality can benefit, but as one sees in this paper, there's a benefit for actually going and combining the outputs of the multiple modalities. And that may very well deliver us the best prediction models. In this case, they were looking at brain age and looking at how relative brain age relates to psychiatric and other phenomena. But there's a whole broad range of questions out there that can be addressed. And when we look to combine modalities, we potentially have the greatest value. And also on the flip side, when we try to translate modalities, we have the chance that even though MRI might have certain advantages, it's more difficult to imagine scaling compared to EEG. And so there's the opportunity to look at what we learn in the MRI and translate to EEG, and also figure out what can't you capture in one modality or other to help make better value judgments. And with that, just of course, there's a broad range of folks that have contributed over the years to the varying data sharing initiatives and data generation initiatives. So of course, grateful to them all.